My name is Amir Khandani, and I'm a faculty member in the Department of Electrical and Computer Engineering of the University of Waterloo. Current wireless systems are one way, in the sense that they use either two different time slots or two different frequency bands to send and receive. Even in the context of OFDM or CDMA, there is no practical method known to use two different tones or two different spreading codes to establish a full duplex link. Full duplex wireless is complicated due to potentially large amount of interference between transmitter and receiver units in a radio. And it's interesting that full duplex communications is used in almost every telecommunications technology, for example, in ordinary phones, DSL, wireless with highly directional antennas, free space optics, fiber, but not in wireless networks. Although the impact on wireless networks like cellular and WLAN is expected to be much higher, because in this context, two-way addresses networking and security issues in addition to doubling the rate. The goal is to connect an access point to several clients. Clients are multiplexed using OFDMA, and access point should support two-way connection over each OFDM tone while supporting the additional degrees of freedom offered by MIMO antenna system over each of those tones. We would also like to support asynchronous clients in the sense that new clients can join the network without prior coordination and without waiting for too long and without disturbing the operation of the clients that are already in the network. I believe two-way wireless will result in major changes in the way wireless networking is done. For example, measurements of actual wireless usage on UW campus shows that the efficiency for about 2,000 clients and a few hundred access points is around 5 to 10%. And the reason is the MAC layer of 802.11. And two-way wireless will solve this issue. Cellular networks have a higher efficiency, but the cost of infrastructure is very high. And as we move towards smaller and smaller cell sizes, the cost will not be affordable any longer. In my opinion, two-way wireless will have a higher impact than previous breakthroughs in this area, like turbo code, MIMO, space division multiple access, and the most recent breakthrough called interference alignment, which was introduced in my own group in 2006, and since then has attracted significant attention. Two-way wireless has been of interest over a relatively long period of time, and there have been some other works addressing this problem. Here I have a partial list of some relevant works, and getting into the details of the literature is well beyond the scope of this presentation. I would like to mention that my initial interest in this topic started in 2004, and I applied for a provisional patent in 2005, and for the actual patent in 2006, and this patent was issued in 2010, and this is easy to find on the web. The starting point for my work was to use multiple transmit antennas to create a null at the location of a receive antenna, and in particular using two transmit antennas with 180-degree phase shift to create a null at the position of a received antenna, which is positioned in the middle of the two transmit antennas. And I would like to add that since that initial idea, I have taken many more steps which I will share today, and these have been subjects of some other patents that I have applied for. And there is just one other point I think I should clarify here in terms of the listed literature, and this is about active cancellation. One of the components behind the performance I will present here is based on using the so-called active cancellation. This means a copy of interfering signal is constructed and subtracted in the analog domain prior to A to D. In general, active cancellation is an old area of research with many reported practical applications. What is new and critical in this work is that active cancellation is done in a way that it does not contradict linearity in the subtraction path. As a result, the method that I will present does not need to have a precise measurement of the cancellation coefficients. And any such lack of precision, which is unavoidable in full duplex transmission, will be accounted for and compensated in the next step in baseband cancellation. As you see, some of more recent references I have listed here, which by the way I came to know after relevant parts in our implementation were completed, also use active cancellation, but their achieved gain due to this feature is limited due to the linearity issues that I mentioned, and we will explain this later in more details. Here I have some more references, and I would like to add that in the process of this work, I have looked at more than 300 references that in one way or other I thought to have some relevance. But again, what I'm presenting here is new, and in my humble opinion, it essentially solves the problem of full duplex wireless. Here I have a summary of some of the novel ideas introduced in this work. One contribution is in reducing the amount of self-interference in the analog domain prior to A to D, and three complementary techniques are introduced for this purpose. After that, digital signal processing is used to further reduce the self-interference. Another contribution is in handling asynchronous clients. Finally, some scenarios for the application of two-way wireless are introduced. These applications show that two-way wireless does much more than just doubling the rate. In particular, this presentation introduces a new way for wireless communications, which is based on changing the channel to embed information, and this is in contrast to the traditional wireless systems which are based on changing the source while keeping the channel fixed. This is made possible if we have access to full duplex links. As we will see, there are major benefits to be gained by varying the channel. Full duplex transmission also solves the bottlenecks that currently exist in practical implementation of many of the information theoretic concepts. An example is space division multiple access, the so-called SDMA, in both downlink and uplink. It makes it also possible to cancel the interference that two neighboring nodes cause on each other. And possibility of supporting two-way asynchronous links with multiple clients also solves many of the MAC and quality of service issues that are currently reducing efficiency and increasing cost in wireless networks. Another contribution is in the context of security enhancement. Wireless is believed to be inherently insecure because everyone hears everyone else. But the same feature can contribute to making the system even more secure. The reason is that in a full duplex system, the two parties transmit at the same time, and this is in essence like jamming each other's signals when it comes to eavesdropping. This work introduces some mechanisms to take better advantage of this feature to enhance security. Another contribution is in secret key generation in the so-called one-time pad, which is the only absolutely secure system. And even in a point-to-point link, by simply feeding back a pilot, we can make sure that the two nodes are synchronized. And lack of synchronization can be the primary factor determining the effective signal-to-noise ratio rather than Gaussian noise. And full duplex node also helps in power control, adaptive coding and modulation, ARQ, to name a few. Here I have a summary of what is new here with respect to my 2010 patent. To start with, I have extracted a figure from the 2010 patent for the design I talked about in the previous slides, namely the use of two transmit antennas with 180-degree phase shift and the receive antenna in the middle. And although this design is only part of that patent, the summary of what is new is with respect to this design. First, some new antenna structures are presented. By using multiple stages of cancellation, it is shown that potential degradation in SNR due to self-interference is virtually zero. I also present methods to support asynchronous clients as well as to support MIMO. In addition, several new applications of full duplex wireless are presented. Overall, hardware and signal processing complexities are very close to the case of a half duplex unit.
Here I have the antenna structures connected to the network analyzer showing a bandwidth of about 30 MHz at 2.4 GHz. The coupling is around minus 60 dB. And my colleague moves the antenna, slight movements, from a distance such that his body doesn't interact with the antenna structure. And we see that small movements can change the coupling in the range of minus 30 to minus 60, minus 70 dB. And this is something we need to deal with. Here I have a closer look at the antenna structures, one horizontal, two vertical antennas, and the total area is about 7 centimeter by 8 centimeter.
RF transmission is based on 802.11 using a 20 MHz channel at 2.4 GHz. Transmission power is about 30 dBm, which is typical for cellular applications. The basic physical layer follows 802.11 in terms of OFDM structure, preamble, synchronization, and issues of this nature. Here I have some numerical values showing typical performance of the system. Antenna structure is the same as what was used in the earlier video clip. Transmit power for each transmit antenna is set to 30 dB, and in total, because we are transmitting from two antennas, the transmit power will be higher than what is typical in cell phone applications. First, we transmit the same pilot from the two antennas without applying any beamforming coefficients. We see that the increase in the level of noise due to the self-interference is about 40 dB. This shows the effect of the interference remaining just relying on the structure of the antennas. Then we adjust the coefficients of the two transmit antennas in each OFDM tone such that they cancel each other at the receive antenna. And this 40 dB drops down to about 2 dB. Finally, after subtracting the residual interference at the baseband, we have small and on the average about 0.4 dB increase in the noise floor. I should emphasize that this 0.4 dB degradation SNR is less than what is typical when transmitter and receiver are in different locations. The reason is that distant units should rely on different carriers and different clocks with possible mismatch between them, and these sources of imperfections usually cause a degradation which is higher than 0.4 dB. In contrast, in dealing with self-interference, we use the same carrier and the same clock for transmit and receive, and we have a precise measurement of timing as well, and this results in very accurate cancellation of self-interference.
Here I have the same antenna structure, but this time is connected to LearTech platform, and we will be looking at different signals in real time in the baseband. The lowest signal shows the transmit power corresponding to the preamble sent from the first antenna, from the second antenna, followed by the preamble sent from both antennas at the same time to measure the equivalent channel, followed by several OFDM frames. And those spikes are the OFDM frames that are transmitted from the two transmit antennas at the same time. This middle signal shows the received power corresponding to the first preamble, corresponding to the second preamble, and finally the effect of the cancellation in the air due to pre-equalization multiplication by the beamforming coefficient to cancel at the receiver antenna. And then on top we have the final cancellation. The top signal shows the effect of the final cancellation, which is the subtraction of the transmitted signal from the equivalent single input, single output channel that we have from the two transmit antenna to the receiver antenna, and we would like to study the effect of different environments in terms of reflection on the performance of the overall system, which is the combination of the cancellation in the air and final cancellation. To do this, my colleague is bringing a metallic plate close to the antenna to change the reflection, and as you see, the signals all fluctuate quite significantly in terms of the transmit power, because the channel coefficients are changed, in terms of the received signal at the two antennas, which show that the coupling can be so quite significantly different. But the final algorithm, or the combination of all of this working together, is able to cancel the self-interference, and we have a very stable performance overall at the received. Here we have a patch antenna including the transmitter, receiver, and the auxiliary transmitter all merged together. Now my colleague brings a metallic ruler close to the antenna to change the coupling, and the lowest signal, which shows the transmit energy, the middle signal, which shows the effect of the cancellation due to the first algorithm, fluctuate quite significantly, but the top signal, which is the effect of the final cancellation in the baseband, has a stable performance.
Here I have some concluding remarks. It is my humble opinion that two-way wireless will have a very profound impact on wireless networks in terms of cost, quality of service, and security in the near future. And it has much to offer, much more than the earlier breakthroughs reported in the area of wireless in the last few decades. An example is multiple input, multiple output antenna systems. In terms of what is next, industry will definitely play the main role in speeding up the developments in this area. And it should, of course, start by including two-way wireless in the forthcoming wireless standards. And I hope that my presentation has conveyed the message that the implementation is straightforward and the performance is very stable. And here I have a set of frequently asked questions that I will update as I receive more. Please kindly send me any questions that you feel would be appropriate to add to this collection.